Welcome to this deep dive into the geometry of statistical separation. Today, we bridge the gap between classical statistics and modern machine learning by exploring one of the most elegant algorithms ever devised, the support vector machine, or SVM. Developed by Vladimir Vapnik and his colleagues at AT&T Bell Labs, SVMs represent a pinnacle of statistical learning theory. To understand SVMs, we must first look at the statistical landscape of the late 20th century. While classical statistics focused on empirical risk minimization, fitting models to minimize training error, Vapnik introduced structural risk minimization. This shift was revolutionary. It's not just about how well we fit the data we have, but how well we can guarantee performance on data we haven't seen yet. This involves the VC dimension, a measure of the capacity of a statistical classification algorithm. Let's visualize the core problem. Imagine two classes of data in a two-dimensional space, let's say blue circles and red squares, representing healthy patients versus those with a specific condition, based on two biomarkers. In basic statistics, we might look for a line that separates them, but there are infinite lines that can do this. Which one is best? The SVM answers this through the concept of the maximum margin hyperplane. Instead of just any line, we seek the one that maximizes the distance between the closest points of the two classes. These closest points are the support vectors. They are the most critical data points. If you move them, the entire boundary shifts. This is why the algorithm is so robust. It relies only on the most difficult to classify points. Mathematically, we are solving a constrained optimization problem. We want to minimize the norm of the weight vector W, subject to the condition that every point is on the correct side of the margin. This is often solved using Lagrange multipliers, transforming the problem into its dual form. Statistics meet quadratic programming here, ensuring we find a global optimum. But what happens when data is messy and overlapping? In the real world, 100% separation is rare. This is where the soft margin and the slack variable psi come in. We introduce a parameter c that controls the trade-off. Do we want a wider margin, or do we want to classify every training point correctly? A high c penalizes misclassifications heavily, while a low c allows for a more relaxed boundary, often leading to better generalization. The true magic of SVMs is the kernel trick. Sometimes data is simply not linearly separable in its current dimension. Imagine a ring of points surrounding another cluster. No straight line can separate them. But what if we project this data into a higher dimension? By using a kernel function, like the radial basis function or RBF, or a polynomial kernel, we can calculate the dot product in a high-dimensional feature space without ever actually performing the transformation. In this higher dimensional space, a flat hyperplane can easily separate the classes. When we project that hyperplane back down to our original 2D or 3D space, it appears as a sophisticated nonlinear boundary. This allows SVMs to capture incredibly complex patterns in data, from handwriting recognition to genomic sequences. Today, SVMs remain a cornerstone of data science. While deep learning dominates in unstructured data like video, SVMs are often superior in high-dimensional scenarios with smaller datasets. According to studies in bioinformatics, SVMs consistently outperform other models in protein fold recognition, where the number of features far exceeds the number of samples. In conclusion, support vector machines are more than just a tool. They are a testament to the power of combining geometry intuition with statistical rigor. They remind us that the best way to separate complex ideas is often to look at them from a different perspective or a different dimension. References: Vapnik, VN, Statistical Learning Theory, 1998, Hasty, Tibshireen, and Friedman, The Elements of Statistical Learning, Cortez and Vapnik, Support Vector Networks, Machine Learning Journal, 1995, James, Witten, Hasty, and Friedman, An Introduction to Statistical Learning.